talking about resonating air columns, and we went through and we talked about how to deal with different harmonic numbers for open-ended air columns. Prior to that, we talked about closed-ended air columns, and so I want to circle back around to closed-ended air columns because what I showed you previously was a closed-ended air column that was dipping into water. You remember I had a graduated cylinder, and I took a glass tube and I dipped it into the water. I had a tone generator that was producing resonance for different lengths. And I have this glass cylinder. All the way across the water, or the bottom rather, this horizontal line is representing for us water. So as I look at this, what I want you to be imagining is that I'm pulling a glass cylinder further and further and further out of a graduated cylinder full of water. Am I solving the visuals on this one? That's what this is the schematic of. All right, so in this first situation, I got myself a tuning fork, and I put myself with a tuning fork over top of my graduated cylinder's glass tube. And if I hear a loud noise, then that means that that glass tube is 1/4 of a wavelength. Now, if I draw this, remember once before, I drew wavelengths, and I drew it like this, and like this, and we remembered that between my fingers right now, that's clearly 1/4 of a wavelength, right? And I'm going to hear resonance for closed-ended air columns when there's maximum pressure fluctuation at the mouth. Now, for those of you that are having a hard time seeing that that's 1/4 wavelength, let me turn it sideways. Can you guys see that it's 1/4 wavelength now? It's just half a hump, okay? 1/4 wavelength, 1/4 wavelength, okay? Give me the nods of the head. Does that make sense? All right, cool. Back to this then. Now, if that's 1/4 wavelength, based on what we've said previously, that must be the first harmonic. So I'll call that the first. Now, this time I printed this out on graph paper. There's a background of a grid that's going to help us with our drawings. Previously, I was trying to get you guys to be a little bit artistic and draw it, with a little bit of artistic flair. If that's 1/4 wavelength, then this must be a half wavelength. See, 2/4. What's the harmonic for this one?
Shouldn't exist.
It's a second harmonic. But we say you're right. Second harmonics don't do anything for me because that's the idea of having zero fluctuation at the mouth, creating a resonance. And that is physically not meaningful. So then we move on to this one. Hey.
Anything? Health and safety?
Nope. We're all health and safety here?
Good.
Thank you. For the next one, I get continuation of that pattern. Quarter, quarter, quarter. Notice I got 3/4 there, 3/4 of a wavelength. Which harmonic would this be if I produced this wave pattern with a tuning fork? Somebody other than the front row. Come on. What is it? Yeah, everybody together says? Third, yeah. All right. So we got ourselves a first. We got ourselves a third. I want to draw the next waveform. And actually, as I do this, I feel like I need to go over some things. This one here was my second. Do it in black. This one here is my next one. Which harmonic is this one? Starts with an F. Yeah, the fourth, yeah. And we say again, that would be a situation where no change in density at the mouth is going to cause resonance, which is physically meaningless to us. So I'm not even going to bother drawing a tuning fork at the mouth of it. This one here, if I put a tuning fork, which harmonic is this one? Yeah, fifth, yeah. So we got a first, a third, a fifth. Notice the second and the fourth are not physically meaningful for us. And then I'll just keep on going. Am I getting this right? Yeah. This one would be our sixth, but again, not physically meaningful because we're talking about having no change in pressure or density at the mouth, giving rise to resonance. So that doesn't make any sense. And then finally, that would be the sixth harmonic, mathematically anyway. And we get this idea that the even harmonics aren't really a thing for us, but we're getting up to a seventh. Now, really, this isn't a seventh harmonic of the same tube because what we're doing is changing the tube. We're changing the tube's length. So this isn't the seventh harmonic of the same thing. We've changed the thing by changing its length, right? But this is an illustration of a seventh harmonic for that particular tube. When I look at this, there may be a lab in your future where you have to figure out the wavelength for this sound wave. And it could be that you know the frequency of this tuning fork because typically that's written straight onto the tuning fork itself. So you might know that's blank number of hertz. That would be something that would be given to you, right? But then when I look at this setup, would you believe that you could take a meter stick and your lab partner could hold a meter stick next to this thing? And if you use that meter stick to measure it at the different lengths at which it resonates, you know, at the first, the third, the fifth, the seventh, you'd hear when it was resonating. And when it gets to that length, you measure it. Now, you measure it from the water height. You don't measure the whole height of the glass. You don't measure from the tabletop. Because remember, the height from the tabletop is always going to add in this extra amount, right? Up to the water line. So what we're really measuring is from the water line to the top of the glass tube each time, keeping in mind that because of water displacement, as the tube rises up higher and higher and higher, the water line is going to change a little bit, right? So you really are measuring from the water line up to the top of the glass tube each time to measure how tall the air column is. I think that makes sense to everybody, right? So if we did that, though, I want to just like map this out. That means that the first length, that is from here to here, I'm going to call it length A. Let's call that length A. I'm going to skip this length, and I want to say that from here to here, notice I already drew in a handy little dotted line. What do you think I'd call that? Length B? Sure, why not? And then I could even do this. I could say, hey, from here to here, length C. And of course, we could do a length D as well, right? So from here to here, I've run out of space on my page, but that would be length D. All right, cool. People say, why would you want to do that? Well, it seems to me that if I do length B, that's the second shortest, minus length A, what fraction of a wavelength extra do I have between length A and length B? You see I go from a peak to a trough, or from a trough to a peak. Let's go back over here. If I go from a peak to a trough, here, I'll pinch it off on this one. What fraction of a wavelength is that? Yep, a half a wavelength. It is, yeah, it's half of a wavelength. So if I can measure length of the air column, length B, minus the length of the air column, length A, then that's going to be equal to half a wavelength. And likewise, if I do length C minus the next one down, length B, look at this. Here's length C, here's length B. Can you see that the difference between those two lengths is also what? Half a wavelength, yeah. I don't want to blow your mind here or anything, but if I do length D minus length C, what am I going to get? Half a wavelength. Now what that means is, if I could pick up the first, third, fifth, and seventh resonance lengths, I could find the wavelength using this pair of lengths. I could find the wavelength using this pair of lengths, and I could find the wavelength using this pair of lengths. If I was in an experimental situation what do you think I would do with those 3 wavelengths? Yeah? Find the mean. Find the mean lambda value. That would be a nice little statistical process for a nice basic lab, okay? Now, at some point, I'm going to give you guys the equipment to do this, and you'll be able to do it. You should be able to find the wavelength for a sound wave inside of a resonating air column. Now, the other thing about this is, if I was somebody who's going to design a musical instrument, do you know that having a place where air can fluctuate on a musical instrument is analogous to having a hole drilled in that spot? Because the air pressure can fluctuate at a hole, right? I could drill a hole there and drill a hole here. I could drill a hole here and I could drill a hole here. And if I line those guys up, you see that that lines up with my A, B, C, D? And it turns out that if you look at any, like a flute or a recorder or something like that, I bet you that holes have been drilled so that resonance can happen for different wavelengths. Now, this one here would play all the same wavelength. And so that wouldn't be a very interesting musical instrument. I bet you could figure out what places holes would have to be for different other wavelengths. And that would mean that when I leave those holes uncovered, pressure could fluctuate at those points, and you'd get resonance for those frequencies. True? And what's more, if I had a hole here that allowed another frequency to resonate, and a hole here, I could blow into this thing, and both of those frequencies would play at the same time. Right? You guys have experienced that with the recorder in elementary school too, right? Totally. In fact, that's why all the holes are there. So different frequencies, different wavelengths can resonate simultaneously. And the whole point of covering those holes up with your fingers is blocking off those resonance possibilities. Cool? So you don't need to know that specifically for this course, but I think it's nice to connect this to musicality, right? And something that we've probably experienced before. But the lab is as it is. But the lab actually is like the foundational physics for how a recorder works. And that's kind of a nice thing to know, okay? They never teach us that in grade 6 or grade 5? Or when did we do recorders? Anybody? Grade 3? Oh my gosh. Every school is different, I guess.